Hey, bud. I'm back yet again.
Good evening, Benji.
What, did you expect me at 12 or 1 like I normally show up at?
No, we're just happy to have you.
Yeah, well, today's a little bit of a whirlwind trip, but,
It's okay.
this is the most that coronavirus is like squeezed out of me. Which is actually like pretty convenient, go to a wedding and then be like, you know what? Let me hide away from literally everyone in the world just so that my potentially foolish decisions don't cause anyone else any other consequences.
Oh, it's
Yeah.
very sweet of you.
And then I was like, oh, wait, but I can see Rob too.
Exactly.
Now that I'm tested negative.
Supposedly.
Tested negative and properly quarantined. But, well, one of the last times that I was here, we talked about what in the heck I have been doing for the last 4.5, 5-ish years of my life, right? Figuring out things about phase transitions and curvatures and stuff. And what I did, obviously, if you've watched the, 3-hour talk that we had, was basically just kind of vomit at you this talk that I took that amount of content and squeezed into 30 minutes. Yeah, that was a good time. Which honestly, like, I mean, from my perspective, I enjoyed it, but
No, it was good.
do you feel like you understood anything that I talked about?
Yeah, of course.
I feel like what we should do is much like what happened in the actual
You
exam.
don't have to shout.
Am I shouting?
Yeah,
Oh my. I'm so excited. get
I
to
know
talk
you
about my
are.
research.
I know.
I figured what I should do is much like what happened after that actual 30-minute talk was to where, the experts listened to me be like, here's all the information that I give. And then in the 2-hour questioning that they had after, they basically went, yeah, but what? I figured we could try that and maybe help illuminate some more about the mechanics on how this actually works and what it actually means. Basically, I'm here to tell you why this picture here is one of the proudest things that I have ever produced in my life, and perhaps the culmination of everything that I've done in grad school.
Well, I see a labeled X and Y axis, so we're off to a good start.
Oh yeah, this might in fact actually go into the actual paper. So, what the heck is this? This is a recreation of a phase diagram for something called the BEG model, Blume-Emery-Griffiths. And effectively what it is our method. Actually, yeah, our method, our concavity method of figuring out phase transitions applied to this particular model. So first up, do you remember how my research works?
Well, essentially, you're using the geometric properties of the density of states to try and determine where phase transitions occur. Basically, wherever you have a sharp transition from one, I forgot what the term you used was, but basically from one phase space to another.
Yeah, so yeah, it's pretty good. From basically so that you could figure out how is there, like, you can use the density of states, basically a property, a thing that any complex system will have that just counts for you how many configurations are possible matching particular measurements that you could want. So for volume of water, how many ways could I arrange the atoms in your glass so that it has this volume at this pressure? That's what the density of states will tell you. If I
Took you 2 hours to explain that the last time, though.
I know. I figured we should like put everything in focus and wrap it up. And one of the interesting facts is that it brings any question of phase transitions down into simply a matter of counting. If I can count the system, if I can count the configurations of the system, then I have a hope of talking about the phase transitions in that system. And that's something that other attempts to extend statistical mechanics hasn't been able to do. That's really the main thrust, the main thing that's really interesting about this type of research is that this mathematical tool is a way of extending statistical mechanics with a viewpoint that's more general than other attempts have been. And not just statistical mechanics, but phase transitions within that, right? Right. The original way that Boltzmann just kind of talked about statistical mechanics and thermodynamics really wasn't very general. It was very much interested in the behavior of liquids and gases, very physical processes. And it wasn't until someone came along later that noticed, well, let's get less focused on the actual physics of it and pay attention to the math that governs that physics and go, well, if I just think about how this math works, the implications that it has on the system, and say, well, no, the math stuff following this math is actually what's more important, then I can use that viewpoint to extend it to these other systems, to these more abstract systems, mathematical systems. Even as we talked about, right, talking about phase transitions in stock markets, talking about phase transitions or the complex system of how animals move across our world, right, from one region to another. You could definitely look at that as a complex system where you're trying to understand how do we, preserve these species by looking at their large group properties. What amount of large rainfall, what amount of clearing or predation do we need to worry about? These are all tools that you wouldn't look at a steam engine and go, yeah, those are the same thing. Those rules apply to the same thing, right? But
I mean, I would.
yes.
But I have the benefit of hindsight.
It turns out that all the water molecules in your fancy steam-powered train are they're just little zebras. The whole world is zebras, migrating from one space to another, looking for, I don't know, little atom watering holes. Yeah. So the idea of finding a more fundamental principle to guide how we derive things is a really powerful tool, right? We've talked about it multiple times on this podcast. It's not only come up in my research, it's come up in this quantum mechanical stuff that we talked about, right? That latest thing about Merman's challenge was all about, like, how does science tell me what's going on here?
So basically generalizing.
Yeah.
Yeah.
It's about coalescing your knowledge and trying to find, the minimal number of principles that you need to believe in, from which you can kind of derive or intuit everything else, right? Our old friend Dr. Gobet loved to talk about the theory of everything, right? You used to have.
He's not that old.
I don't mean old in the sense of him being old. I mean in the sense that I haven't seen the guy in forever, and we need to do that road trip.
Oh, it's happening.
So, right, he really put it in terms. I think this is a common thing, right? You can look at the universe and really kind of derive it from about a page of different equations, right? You've got the equations of the four different forces, and so really it turns out you can crunch them down into the three forces: the electromagnetic force, the strong force, and the weak force, at the most basic level, crunch down into
19 equations.
Yeah, something 19 equations, something all basically determined by quantum chromodynamics, right? The extension of quantum electrodynamics, which is the extension of quantum field theory, which is the marriage of special relativity and quantum mechanics together. Because we can at least get that much. Now, the moment you take space-time and you bend it, and you're like, yeah, but what if gravity? then you're like, oh, I can't, in fact, do anything. But those 19 equations measure those three forces, like determine how those three things will interact. And then you have gravity coming along as this fourth final force that we all fortunately feel. Thank you, Earth. Thank you, atmosphere.
But to be fair, it's so weak compared to the other three forces that unless we're talking about very large objects, it can generally be disregarded for most things that we're looking at.
Which is why quantum chromodynamics, even though it can't capture gravity properly, it's still the most accurate thing we've ever produced as far as theory goes, right? You get predictions that are accurate to the 14th decimal place or something, which, let me tell you, as a theory boy, that's insane. To be able to sit down and be like, oh yeah, I know exactly how this is going to measure to more than 10 orders of magnitude. Oh my goodness. That's
Yeah, and considering modern medicine, for instance, you'd be lucky. Like maybe setting bones, we can get into the first decimal point.
yeah.
You know,
Yeah.
anything more complicated than that.
Right. The most blunt and obvious thing of like, how do we fix the human body? It's like, well, I can predict they should be like this, right? We can get just that close. But, you know, if the moment you try and abstract it, like, okay, how do we treat a disease? How do we, you know,
What is a
attack
disease?
cancer?
Is a disease in all people?
It's,
Yeah.
I mean, that's a fun bit of the extension of, you know, emergent behavior upon emergent behavior, right? The famous quote is everything is physics, or excuse me, physics is the only important thing. Everything else is stamp collecting. Thank you, Rutherford. Look, the 19th century physicists had some real high opinions of themselves, which, to be fair, the OG physicist, Isaac Newton, did in fact love to get into just the biggest, dumbest beefs about how his system was the best and how other physicists at the time were dumb. And yeah, you know, that quote, we stand on the shoulders of giants, was a dig at Hooke.
We see further by standing on the shoulder of giants.
Yeah, it was a dig at Hooke because he didn't like Hooke's law, which encapsulates harmonic oscillators, right? Which it turns out physicists look at that tool and go, yeah, no, the universe is harmonic oscillators. Everything you ever do, if you ever take a serious science class, it's just, oh yeah, so here's the harmonic oscillator in this form, in this system. Everything. It's one of the most basic approximations that actually starts to capture behavior. So it turns out Hooke was right. Anyways, so to get back, right, even though like right now we have a decent thing on three forces, and we have a very accurate theory for predicting three of the forces, and we have a very accurate theory for predicting the fourth one, gravity, general relativity. And when I try and write all those down, I can write down all of that onto, like, you know, maybe a page or two worth of equations. And yes, working with them is difficult, but at least the lensing of what matters and doesn't, that's extremely important. That's it. I don't think it can be overstated how important it is, the way that you look at things, the lensing that you bring into trying to understand or problem solve, right? It makes a huge difference, right? If I'm trying to, right, one of the perfect examples, I think, is archery. And you know the way that they measure success, right? When you're first learning, well, even when you're not, you take your arrow, right? You've got your bow and arrow, and you're shooting at the target. And anything that's not a bullseye, it's called sin. You've failed. You've missed the mark. And it's not about how close you get, it's about hitting it. And that makes some really accurate archers, right? The lensing that they bring into their profession, into what they're doing, their sport, is incredible, because it's like, no, we must make the target every time. And
bowling, professional bowling is pretty much that as well.
Yeah. Anything. Right. Well, that's a fun little game of like exponentials. Like, oh, you get off by one pin. No, you go from getting close to your top score to just like a horrible score very quickly. What a good time. Right. And the lensing of those 19 equations, or so, you know, that page of equations that we can currently write down to describe our universe, is extremely important. But it would be really cool, and perhaps even more enlightening, if we could develop a theory of everything. Because at that point, what you could do is you could take that whole page, and you know what? It might still be a page long, but instead of 19 different things, it would be one thing, one equation that would tell you, yes, this is how everything interacts together.
So can't we just take those 19 equations, slap a little coefficient on each one of them, and put plus signs?
I mean,
isn't that our theory of everything?
Oh boy. I would love to say that we could do that, but also no. Very much no.
Okay.
I mean, the the way in which the two systems interact, right? We've talked a lot about quantum mechanics, and there's an inherent fuzziness to what happens when you try to actually talk about measuring something. When you try and say, okay, when I look at the universe, what am I going to see? There is a fuzzy bit of probability that pops up in there. That's a topic for another time. But it is fundamentally incompatible with the architecture of general relativity. That so much to the point that if you try to put little coefficients and add them together, you lose all meaning of what you're even trying to do. It would be like if I asked you, how long is your daily commute? Because that's an important, interesting thing. And you tell me, well, it's about 35 pounds. I go, what? That's nonsense. And you go, yes, 35 pounds. I meant it.
Maybe that's what your toll fares are.
It could be. But the problem with trying to, at the moment, fully integrate these two is that they lead to fundamentally incorrect predictions on what you should see out of the universe. Just even on what's the right word? Epistemic, not existential. Basically on an assumptive level about what you assume the world, like where you're even starting when you bring into it. Well, that's a bit far off the beaten path. The important piece is that having the right framework for understanding what's actually going on here can be incredibly powerful. It can allow you to take ideas that you think would be very different and realize that no, they are explained by the same or perhaps different lensing of the same aspect, the same fundamental object. And that's kind of what our research, right, is going about. You don't have to worry about understanding necessarily Hamiltonians. You don't have to worry about understanding all of the complex behaviors or even worry about maybe capturing all of them to see if you could have phase transitions with your current understanding. All you have to be able to do is count the configurations that you could have. So all of this complication that you might have to worry about if you're trying to do the usual statistical mechanical extension of those tools to your new non-physical systems, and then try and figure out, okay, how is this vast complex system, all of these small interacting parts, what's the bulk behavior going to do? And then you're going to have to worry about somehow figuring out the variables that matter to figure out, oh, well, if I just, nudge the temperature of the system, or I nudge the rainfall that the zebras see, all of a sudden, instead of going, across the Serengeti to the Congo, they move north and they end up in the Sahara and starving or something, right? And you know what? That would be something that would be, obviously for the poor zebras, incredibly catastrophic. And that would be something that's like, hey, maybe we should be able to predict that properly. But, right, if I want to study, that complex system, it's going to be important to be able to accurately capture those wild shifts in behavior. And that's all about what that research has been. Is if you can count it, you can look at how that counting function occurs, and from there we can talk about when these splits will happen.
Now, to be clear, when you say we can count it, this isn't necessarily counted empirically. This means if you can just pre-generate all the known configurations ahead of time, that you don't even need to have any empiricism there, because you've just brute forced. Not that this is easy in all problems, but you've just brute force mapped out every possible state.
Yeah.
And then just using that, you can then determine where the phase changes would occur.
So like that falls back into its strength. It's that even though brute forcing something might not be easy, in theory, it's possible. It might take, the the lifetime of the universe, but ignore that. What matters is the principle of it, right?
Mm-hmm.
And if you can, brute force it, you can get access to where these phase transitions show up.
Well, I'm thinking in medicine, right? There's going to be circumstances where it wouldn't be ethically possible to empirically determine everything ahead of time.
True.
So you would have to just, now granted, this is far into the future when we have the computing power to do this, but you would have to basically use a density of states approach.
Yep. Now, getting to there might be a bit difficult, right? Because that's layers and layers of emergent behavior. It's great. But so the picture that I have shown you is when you have these transitions, these differences in behavior, there's two main things that you want to really be able to capture, which is if I have a glass of water, right? The transition from ice to liquid water, right, as I warm it up, is actually a first order phase transition. Because what happens is I have to take the ice and I have to warm it up to melting temperature. But once I've got that ice at 32 degrees Fahrenheit, I actually need to keep pumping in more energy before the temperature of the water increases. Because what happens is that it takes energy to break the bonds the water has made with itself for that to make a solid structure and change into the liquid state. And that leveling, right, if I increase, as I have energy, as I increase energy, the temperature I'll have a stair step, right? It'll increase in temperature, the ice cube will, then it'll melt, and then the water can increase in temperature. And that flat part there is very indicative of what's called a first order phase transition. There's a break in the property, right? There's a break in how in this smooth transition from one phase to another. That actually shows up in its specific heat. That shows up as a divergence, where it goes here and then jumps, right? Based on the temperature that you can get the water to, right? I guess measuring that as a function of energy would be crazy.
So now is a sublimation also first order?
Mm-hmm. Basically, every transition you would have with water would be first order one, I believe, because there will be some amount of energy that has to go into changing the structure of the bonds between the water molecules, whether that is going from the solid, the very strong bonds between solid water, breaking that directly into gas molecules, right? That requires a lot more energy. Now, off the top of my head, I don't remember exactly the right process. Obviously water to liquid, the normal freezing and boiling are easy because, we can do that. Those are what we experience every day.
Oh, the phase graph of water. If you pull it up while we're talking, sure.
Yeah. Right. There's a triple point that pops up with it where you can, I actually saw a wonderful GIF of this of water going between all three states of matter all at once, which is a really unique property of water. And we're I've seen the case made that because that's possible, that's why life exists, right? Without it, it's one of those far-reaching things. But still, if you didn't have that property, a lot of the stuff that makes like all of our higher order biomechanical pieces kind of falls apart. The important piece of that is that this is different from, say, for example, the transition for a piece of iron when you magnetize it, right? If I have a magnet, right? I have a piece of iron and I stroke it with a needle, right? Eventually, as I stroke it, the poles that are, all the, basically the little magnetic dipoles that are quadrupoles that are the iron atoms, as you stroke them, eventually will all align in the same direction and the magnet will become magnetized, right? That is what's called a second order phase transition because it happens smoothly. The amount of magnetization in that bar of iron is a continuous function of how many times I strike my needle, aligning, dragging along.
So there's a linear relationship with input
Mhm.
and output?
Yeah.
Okay.
Even if it weren't quite linear, it would, well, it depends on what you graph. So
Okay.
let's not go, let me not put my foot in my mouth with some inaccurate information there. But
there's not going to be a step function.
Yeah.
Like any input amount is going to correspond to a different output amount.
Mm-hmm.
Whereas the first order, you could have multiple inputs that would belong to the same output.
Right.
Okay.
Right. So here, right, the triple point, that bit in the middle there, is exactly where you can go find. It looks really weird. You've got water freezing and melting and boiling all at the same time. It's nuts. But the basic idea is that as you, right, when you're trying to do thermodynamics mechanics, it's important to have these pictures that tell us where do things break down or where do things shift based on the external properties that we have. In this case, right, I'm measuring temperature and pressure for my system for water. And because I have literally this information, we were able to create a steam engine. We were to figure out how to turn the changing of heat into force, right? Into, forward force, motive force. Yeah.
Mm-hmm.
And yeah, a lot of really cool stuff. Also, yeah, supercritical fluids. That's really interesting. Eventually, the notion between liquid and gas breaks down. So that's that second critical point there. And you're in a real weird world where it's all the same, liquid
And if I remember correctly, don't we have supercritical fluid in Saturn's core? I'm trying to remember.
Oh.
Or it's just metallic hydrogen. Maybe it's not water, it's metallic hydrogen.
It could be. I mean, as long as it is, in fact, hot enough and high enough pressure, then bam, there you go. Supercritical fluids.
Oh.
Did it work?
So anyways, second order.
Yeah. So, and that difference between what type of phase transitions, right, obviously makes a huge difference. If I didn't recognize that
Well, I don't think most people would even consider the magnetization of iron to be a phase transition.
Mm-hmm. Oh,
They would just assume it's just a property, even though a phase transition is a property, but they wouldn't think of it the same way.
Yeah, so that's that is one of the difficulties of doing this is almost how philosophical you have to be. Right? What is a phase? Hard thing to answer. But that's almost that it there are plenty of things that we intuitively deal with that it's really hard to pin down when you try to sit down and be like, oh, well, what is this actual thing? Right? Well, I mean, most obviously, matter. The heck is matter? We don't know. We just know how it interacts. One less common thing that people might not have thought of is the idea of dimension, right? The notion of how we can move, right? I've got 3 dimensions. Most people are very comfortable with that. But the moment you take a step back again from physical systems, and actually even in physical systems, the notion of what a dimension means, whether it's degrees of freedom, whether it's the space in which you have things to interact with, because you can, as you abstract, right, the notion of motion and translation kind of goes away. There's evidence that, what is it? The ways that neurons in your brain, for example, follow hyperbolic geometries. And so like that idea that your notion of dimension entirely different from the 3 dimensions that we, categorically think like, oh yeah, I just can out, in and up and down and back and forth, right? Easy. The moment you take
The whole concept of a geodesic, even.
All right, moment you take a second to look into like, but what is this thing that I'm discussing? It gets fuzzy, right? So, where were we talking about? We were talking about water. Obviously, this method here has a huge way of being able to be extended, and one of the important factors is being able to distinguish between first and second phase transitions. If you're ever going to talk about phase transitions, that's a fundamental thing you need to be able to do. You need to have a notion, because obviously if we didn't recognize the water was a first order phase transition, we wouldn't be able to make the steam engine, right? Knowing that you need to heat up the water, not just to a certain temperature, like, it takes this much energy to heat up water from liquid water to steam water. It's like, no, you need this extra chunk. And then once you go put in that extra chunk, oh no, look, the pressure has changed from what you should have. And then everything falls apart, right? If we weren't able to account for that, things would be bad. But what if I have a second order phase transition? Well, I need to know the difference between those two types of transitions that occur in those two different systems. If you remember my talk from last time, right, where we kind of went over some mathematical models, we went over stuff with some, well, I mean, they're all mathematical models, but we talked about the ideal gas and van der Waals gas that kind of has a phase transition that it tries to capture. We went over some graph theoretic models where you sample different graphs. Really cool stuff. All of those phase transitions that we saw in there, exclusively second order phase transitions. There's no shift in what's called latent heat, right? For when I'm melting ice, the amount of energy I have to put into to take the ice that's at 32 degrees and then melt it to water that's at 32 degrees, that energy is what's called latent heat. And it doesn't show up in the models that we discussed before. But that picture that I showed you.
Well, I was about to ask, what about the one with the critical point? Even that's a second order phase transition?
Yes, because it was a second order critical point.
Second order critical point, okay.
It's a smooth, yeah. So if you remember that picture, right, if basically you change the parameters on that, if I move into that, the way it would sample the high and the low density graphs, you would see it smoothly spread out from that, from outside the critical point to when you go into the critical region. If I have a first order phase transition, then effectively what happens is that a peak in the phase space, a peak in the phase that I sample from, appears at a large distance away. It doesn't smoothly break off. Well, we'll get into that. But there's also like a shift in other parameters. And this, one of the best ways to capture is, well, let's look for a model that has first order phase transitions and see if the method that I'm proposing actually describes phase transitions properly. Let's see if it can actually capture that, right?
Okay.
So that's where that picture came from. The picture that I showed on there earlier with the thank you Python for your terrible color schemes. It's fine.
You could change them.
I know, but sometimes you just gotta go, hey, I did this for research and let's just talk about it. I don't want to think about changing parameters just for another hour fiddling with options. Yeah.
Well, you still got that puppy open. You want to pull him back up?
Yeah, this guy here.
There he is.
Yeah, so this comes from something called the Blume-Emery-Griffiths model. It's a mathematical model that is trying to capture the superfluidity that appears in liquid hydrogen.
Oh, okay. We just talked about that.
Yeah. So there's a difference between the supercritical fluid and superfluidity.
Okay.
So if you bring down the temperature of something enough, right? Well, actually, it depends. Helium is weird because no matter how much I freeze it, if I could take a bunch of helium and drop it down right down to zero temperature, what do you think would happen?
The entire universe would end?
Well, no.
I mean, that's literally impossible.
So let's say, fine, I can't get it down to zero T. pick for me a number that's as close to
Right, right.
0T as you want.
Some vanishingly small
We
fraction
bring hydrogen
away from zero. Correct.
We set some liquid helium we set some helium down to a temperature of epsilon. Are you happy now, Rob?
Yes.
What happens to delta? Tell me your analysis.
Well,
what did your real analysis teach you?
I mean, the only thing I would be comfortable in saying is that there's probably not a lot of kinetic energy in that molecule or that atom that we've slowed down.
Right. Yeah. A fun bit. Thermometers are just speedometers for atoms.
Right.
So, what's interesting about helium and hydrogen is that when you bring them down really, really low, our normal intuitive thing of water, well, I bring down its temperature, right? This is what science is we look at something and we go, hey, there's a behavior here that kind of acts like that, right? I look at this, I bring it down to a cold enough temperature, and then it becomes a solid. Oh, that's really cool. Well, not everything does that. Right here, water, if I bring it down to the temperature, it becomes a solid, bulky thing because there's, by whatever magic that makes water, it's configuration of hydrogen and oxygen, the bent and the atomic angles, allows for that structure. But when I have helium or hydrogen, the fact that basically there's not enough bonding material on those particular atoms, they can't drop into a solid state. The best you can do is get a really, really dense liquid. Well, sort of. Except if you drop it down cold enough, there's a new state of matter that pops up, an entirely quantum mechanical one. It's called a Bose-Einstein condensate.
Right.
Right. I don't know if helium has to be dropped down entirely to reach this, but it's close. And so what's interesting about Bose-Einstein condensate is that effectively, as you drop the temperature down enough, the wave function of the atoms kind of spread out, right? If I drop down the temperature, I'm very, very much knowing, I'm limiting what the momentum of those particles could be, right? And since I'm limiting what the momentum of those particles could be, I'm more accurately knowing what the momentum of those particles could be.
But at the same time, the position becomes fuzzy.
So, because of the Heisenberg principle, there's a fundamental relationship between different measurements for momentum, its position. So the wave function of the helium atoms for their position starts to spread out. And there's a magical thing that if you make it spread out enough, all of the atoms that make up that bulk of liquid all of a sudden join into the same wave function. Basically, it's like all of the atoms that are in that liquid are everywhere in the liquid all at once. Everywhere confined within the volume of it. I don't know if you have to go all the way to a Bose-Einstein condensate to get this, but definitely this leads to that behavior of what's called a superfluid. And what happens with a superfluid is the viscosity disappears. There's effectively no resistance to flow within that liquid, right?
So you said it's spinning and it's just going to keep going forever.
Yeah.
Basically.
It's right. You think about I put my finger,
other than the drag against the side of the glass, but
yeah. But if I try and run my hand through water, if I'm in the boat and I put my hand and we're driving through, oh wow, my hand gets yanked back. If I try and push my hand through a vat of honey, right, it really sticks. That's viscosity. It holds on to you. It's a resistance to motion through it. You try and do that through a cold enough vat of helium, you feel nothing. I mean, mainly because your hand is just frozen off. But as I move through, I go, there was no resistance to the motion of my hand through that liquid. And this model is effectively trying to capture that because it actually depends on the mixture that you have in this helium, whether superfluidity pops up or not, or where it does.
What do you mean? It depends on the mixture.
So, just like how we think about atoms on the periodic table, right? As you're moving around on the periodic table, you're changing the number of protons that are in the nucleus for the
Oh,
electrons.
so you're
right?
talking like isotopes?
Yeah.
Okay.
So if I don't change the protons, but instead change the neutrons that are in there, I'll have different isotopes of that atom. And it turns out different isotopes will have different properties. Effectively, because you're changing the number of hadrons, the number of spin particles that are there, you will have either things that act kind of like bosons, or like collectively kind of like bosons, and things that collectively kind of act more like fermions. And so here, this model is capturing a mixture between helium-3 and helium-4. And helium-4, completely inert, has no overall spin, but helium-3, I believe I'm quoting this correctly. I might have gotten it swapped. Helium-3 has a magnetic moment in the liquid. And so the question is, okay, where does this collection of helium shift from being paramagnetic responsive to the external magnetic field that it could have, and from ferromagnetic to paramagnetic? Because when it shifts to paramagnetic, it means it's rejecting the magnetic field that's trying to go through it, and that is when also superfluidity happens to pop up.
Okay.
Right? Yeah.
Now, this is opposed to diamagnetic.
Yeah. Again, to be fair, those are details of the paper that's just like, oh yeah, here's this phase transition that occurs, and I'm like, I don't care, just give me the phase transition.
Right.
If you want someone to really tell you about everything of the different types of magnetism, right? We need to fly Kristen over.
Call Kristen, yeah.
San Francisco. Yeah. But so we've got this model.
I think she's URI. Or not URI. Yeah, University of Rochester.
Oh, is she there?
Yeah, Rochester.
Rochester.
Yeah.
Fun. I'm bad at Facebook. Sorry, Kristen.
It's okay.
Anyways. So, how does this thing work? Well, we're going to terrify the audience because I'm going to show you
Math time?
Oh,
wait. You said proofs. That's even worse than math.
No, I'm going to show them some science papers.
Oh, cool.
Yeah. So, as we've kind of discussed before, statistical mechanics really is happy if you can give it a Hamiltonian, right?
Mm-hmm.
If I can give you how much energy is going to be associated with this thing, then I'm going to be really it's going to be really easy to figure out all of the statistical mechanical mathematical objects that you would want.
And again, to summarize, it means if we can measure the energy,
yes,
system at a particular point.
Absolutely.
Right.
To put it in, human terms. Excuse me. Robot here.
I remember in undergrad, it was funny because you could tell when people are just first starting to learn it because they're always like, oh, I took the Hamiltonian. It's like, oh, they sound so pompous. There's like no way to say Hamiltonian without sounding arrogant until it becomes like 5th or 6th year. And then it's like, yeah.
It's so good. No, it's just a thing.
It's just a thing.
It's just a thing. Right. So here, this is the paper that we're going to, that I'm going to work on. Specifically, because just like how we had earlier, a phase diagram that popped up with water, right, showing you, oh, okay, this line is where liquid water and solid water commingle, and this is where liquid water and gas commingle, and this is where it loses meaning, and above is where you get the different phases. This paper is basically looking at the mathematical model of the BEG, Blume-Emery-Griffiths, and saying, oh, hey, we can map out the phase transition that happens, and we can actually...
Now, what exactly is BEG again? I know you've said it.
It's the 3 authors that came up with it. Blume-Emery-Griffiths.
It came up with it. This is the technique that we're talking about?
Came up with the idea of the model. Just like how the model that we use to try and model magnetic behavior is called the Ising model.
Mm-hmm.
It's not called that because physicists were like, yeah, we love cake.
Right.
Magnetism.
It's not even spelled that way.
Magnetism. Magnetism is like frosting on a wedding cake.
Right.
Or if it's the better kind, you've got buttercream. And we want to map out the transition between those two types. No, of course. Physicists are instead more interested in, I guess, cataloging, and not always the greatest with their name, minus the acronyms that the astronomers come up with.
Yeah, we have the best.
Those are pretty good.
Yeah. Absolutely.
But in general, right, the most common kind of naming convention you get for models and stuff is not, well, what are we trying to capture? Because, and you can understand this, right? Because, well, maybe someone else comes along with a better model that overtakes the old model. Well, you don't just want to call it the same model, but like version 2.0 or whatever. You don't, right? So
this isn't computer science.
Exactly. So instead, we name it after the people that, initially propose them as a method to study the things that we want to look at. So, Blume-Emery-Griffiths said, "Hey, here liquid the superfluid transition and liquid helium is really important. Here is the thing that we think can capture it." So basically, it kind of relies on this Bose-Einstein condensate thing that I was talking about. Is effectively, you say you have in spin sites. Basically, you have, let's say I've got 50 atoms of helium. And when they're really cold, when they're in this Einstein condensate situation, since the wave function says that every atom is basically over top of every other atom, they're all interacting with each other all at the same time. They're all in the same place within that volume all at the same time. So any spin, whether it's spin up or spin down, or in this case, it could also be spin zero, right? You can have the helium-3 that can be oriented up or down, or you can have helium-4 that just has no orientation whatsoever. Each of those spins are able to interact with each other equally well, and there's no notion of the configuration that those spins are in.
So no crystalline structure forms or anything.
Right. Like with the Ising model, the fact that there is structure, right? That the magnetic dipole of one atom can only interact with its neighbors. Not only, leads to a different phenomenon, leads to this magnetic behavior. Interestingly enough, it also really complicates the math because, well, yeah, basically, as a side thing, it's really easy. It's really easy to count if all you have to do is just keep counting plus one. But if I ask you, all right, count all the prime numbers, but only the twin prime numbers.
Oh.
But now only the twin prime numbers that are that are at least, right? Like, even if you had that list of all possible prime numbers, right? Or if I just said, I don't know,
an infinitely long list.
Yeah.
Supposedly.
What if I asked you to count the multiples of 7 or 7 plus 2, or when you try to count things but selectively count, it becomes so much more difficult. So we could have configurations in the Ising model that's like, oh yeah, here I've got this thing. It's like, no, but that doesn't actually match the properties you're trying to. So you can't actually count this particular configuration. It's gone. It doesn't matter. The labeling doesn't match up. And it makes the process of counting it really hard. And that can either come with actual physical counting, or that can come in the form of taking into account the energy contributions in the Hamiltonian, the energy function, right? Yeah. And that's actually what makes this model calculable. We can look at the energy in the BEG model. And this is where it's going to be, this is where the notion of you have helium-3 and helium-4, that strength, the mixture of it, playing a role. Each spin site can be spin up, spin down, or spin zero, depending on the type of isotope that's in there. And since, well, let me get to that. So when I want to know, well, how much energy is in a particular configuration or a particular choice of like, okay, the first atom is up, the second atom is down, the first atom is up, the third atom is 0, the fourth atom is 0, blah, 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 until I get to the 50th atom, because we're going to say we've got 50 atoms in this thing. Well, what I would do is I would say, okay, how many of them have actual spin to them? So the ones that aren't spin 0, let's just add all of those up and say that they are multiplied by some coefficient that says, okay, the amount of energy contribution from that is this, right? And when I want to add that up, the fact that each site interacts equally with each other site means that all I have to do is do a simple sum from my first atom to my last atom. And I don't have to account for anything else. If this were the Ising model, you would have to be like, oh yeah, let's see. So sum over I such that I plus I1, I plus its neighbor would be all of this.
Because they're all interacting with each other. Right.
And it makes trying to take the sum or even discuss that sum incredibly difficult. I cannot describe to you how hard it is. Having done a little bit of stuff in the 1D Ising model for the talk that
Didn't
we
you
did
say
before.
the 3D Ising model was impossible?
Yeah, 3D Ising model is provably MP complete.
Right.
1D is trivial, and 2D, it's probably MP complete as well. But when I was looking through the literature, I couldn't find anyone specifically saying that. There's a definite proof that 3 or above is just impossible.
Maybe there's a Millennium Prize for that or something. Or what was it? The Fields Medal? I forgot. What's the math prizes?
So there's a Millennial Prize, which are the 7 most important things of the 19th century. At the end of the 19th century. Or no, at the end of the 20th century, excuse me. I hate how we count things. Great, because it's my job. Then there's the math version of the Nobel Prizes, which is the Fields Medal, and then obviously there's the Nobel Prizes, because a fancy, rich Swiss man was like, yes, I want to reward these fancy scientists.
Dynamite.
Absolutely.
And contributions to humanity.
Basically. All right. And so the energy is determined by how many of my atoms have a spin to them, because some of them can't. Some of them can be 0, right? How many of them are either pointed up or down? The squaring means if it's negative, it just, negative times negative is positive. So it's all positive contribution. And from that, I subtract a scaling factor. Again, this is a coefficient that determines basically the strength of this thing here. And this thing is just the straight up magnetization. How many ups do you have minus how many down oriented ones you have? And then you take that number and you square it. So this produces a symmetric function. So the amount of energy, it doesn't matter whether it's oriented up or whether the overall magnetization is oriented down. And it shouldn't, because, whether I hold a magnet like this and its effects versus whether I hold it like this, right? The only thing that really matters, it'll look the same, me swapping my hands or me turning my head to look at it a different way. Right. So it should be a symmetric behavior. Right. So, yeah. And that is the energy that pops up in this system. So if I tell you how many, or obviously you know how many atoms there are. So if I tell you how many of them actually have a spin at all, right? And then how many of them are spin up, I can determine their energy, right? From that, I can find everything else, right? Because, I can take, the total number minus the ones that are spin up, that gives me the ones that are spin down, and this only cares about the one, right?
But you told me earlier we don't even need the Hamiltonian.
We don't, in theory, but here it makes it convenient for getting the density of states.
Okay.
I know. I promise big things, and then I go, yeah, but I can use the old stuff as a crutch.
Okay.
Look, we're at the point of proof of concept, and here we capture all this really neat behavior, even if we have the same crutch as before. it's a whole nother thing to be like, all right, let's figure out the density of states.
So
of
we're
zebra.
pouring the Coke that we've been drinking into our radiator so we can limp into the auto shop.
You got it, buddy.
All right.
Hey, look, there is nothing wrong with taking advantage of the easy mechanisms that are already provided to you, right? We don't necessarily care about how we get to the density of states. I just want to say, hey, if you have this, I can capture everything that you ever want.
Right.
Speaking of, if I want to talk about everything I ever want, well, we got to go down to this guy here. So this is the phase diagram that this author, Barr et al., Gamal Rufo, was able to put together, right? They, interestingly enough, they looked at an object similar to ours. They were able to, the density of states. From the density of states, they looked at the entropy. And then from there, they said, hey, here we can look at when these coefficients A and B go from positive values to 0. That's indicative of these different phase transitions. Basically, because what they're doing is they're looking at the where did he put it? Yeah, here. So entropy as a function, basically as a Taylor
Up a little bit.
Yeah, you're right. As a Taylor expansion around magnetization. Well, when the coefficients of these change,
are you able to zoom in a little bit too?
I should be able to.
Yeah, there we go.
Yeah, that's a good call. So when the coefficients of these phase transitions change, right? So in particular, it starts at saying like, okay, these are negative, and then at a certain point, this goes to 0. That's going to be a second order phase transition. And then this, when this is also 0, that'll be your first order type phase transition.
So when A goes to 0, it's second order. When B goes to 0, it's first order.
Yeah. And effectively what is capturing is that, right, the entropy, which we kind of can think of as the amount of disorder, right? How much knowledge do I not know? Or if I look at a particular, like if I take the model and I say, okay, let me look at it, how surprised am I at the result? How surprised am I to find that there is some magnetization here? Right? That's what this function is telling me, right? Because it's these coefficients and it's all a function of magnetization. Because I expect that if the helium has no magnetic field around it, then I would expect it to have 0 magnetization. So then if I look and I go, oh, look, there is a little bit of magnetization, I'm a little surprised. And because of the nature of, statistical systems, you're going to have a little wibbling.
Occasionally, right? Yeah.
What's important here is the behavior of your entropy to the amount of magnetization you find, right? If I have this as some negative number and I have B as some negative number, well, when A goes from being negative to 0, the amount of surprise that I have to seeing some magnetization hasn't just, changed by a little. It's changed fundamentally because I'm not getting as much traction. I'm actually like not as surprised, right? I have more information. And so that's a phase transition according to this, right? We've shifted from, look at this paper here. We've shifted from.
So basically a high entropy moment is a phase transition.
Well, it's the responsive entropy to your conditions, to what you see. So if my entropy decreases, if the amount of surprise that I have increases faster than I expect, I've had a phase transition, right? Effectively is what they're arguing here.
Okay, so it's not just it's a high entropy moment. It's the entropy has diverged significantly from the expected value.
Right.
Okay.
Based on what you actually expected.
Okay.
Yeah. Yes. It's not the entropy itself, it's the response of the entropy to whatever magnetization you actually observe.
I see.
Yeah. So, the way that we naturally have control over this is that I have control over two things in this model. I have control over the mixture of how much helium-3 or helium-4 I have, and that's quantified in this system by the delta function, by this delta coefficient, which if we look back to the Hamiltonian, that's the thing that multiplied the sum of all of the particles that just have any amount of spin to them. So, right, if I change the mixture, right, the response that the system will have is basically going to follow according to this. We capture that sensitivity with that coefficient. Right, that's the idea.
Okay.
The next thing I will also be able to do, which I can most easily do, is it's really hard to, force a system to have this much energy. I want you guys all together to have this much energy in your spin and your magnetization. Really hard to do that. So instead, what I normally have control over for my environment is I can push the button on the thermostat. And that's what our axis over here is that I'm looking at my temperature, right? Now by changing temperature and multiplying by kVt, I have an effective.
We had this conversation before. It's like, what is the difference?
I have an effective temperature that it's in equilibrium with, but that doesn't mean that I'm setting the temperature of the system. I'm setting the average temperature of the system.
Okay.
Right. And what this line here is from here on. So if I have, this combination, and we're effectively dividing out the constant that determines the strength of the systems, the response to it, according to magnetic response. Effectively, what you could do is just say, since, right, the response of the system to magnetization will depend just on the fact that it is helium, right, that you're mixing, right? It doesn't matter that it's helium-3 or helium-4, it's just the helium atom. J will be a number. We just don't know, like, without looking experimentally what number that will be. But if I divide it out here, I can basically say, let's have J equal to any particular number I want. It won't change what this graph looks like. Right. So my work, right, when I'm doing this, I'm like, we have a model. We have a universe where helium's J is equal to 1. And if it's different, well, we can.
So you're telling me the energy doesn't matter?
It will, because J is not 0.
Okay.
Right. It's just equal to 1. The magnetization will matter, but I don't want to have to. If I changed J, this would have a third axis, and then I would have to figure out how to, map out an entire 3D structure and then show it in a paper, as opposed to a nice convenient little
pick a J and stick with it.
Yeah, 3D printout. Because at the end of the day, it's not going to matter to the dynamics of the system that we have, right? Since we're working with a particular atom, the J will be the same always. So you can just kind of divide it out.
Okay.
Right. Particularly once I look up here, if I have this delta and temperature, as I drop down here, this line means I go through a second order phase transition. Basically, according to this paper, that's where up here we have both A and B are negative. Then here A becomes 0, and then I'm in a place where things are all spiky. I'm like, if I follow this line down, I get to this little guy here. This is the tricritical point. It's the transition point where if I go a little further past here to the solid line, the transitions that you get when you cross here are first order phase transitions. So we have a system, a model, that exhibits both the first and second order phase transitions.
Okay, so what we're saying is when energy is below a certain threshold and we increase and decrease temperature above that dotted line, then we're observing a continuously smooth phase transition. And then once we reach that tricritical point, we've added enough energy to the system. Now we're suddenly...
Not the energy. This delta is not energy. It's the mixture of helium to helium-3, helium-4. Basically, you've got enough response to the overall magnetization, the overall...
the J is... I'm so stuck in joules. I am like, okay.
it's annoying. I know it's annoying. It's a convention that's there for a reason, but it is annoying.
Okay.
Yeah. So as long as my response to the amount of magnetized particles is small, I'll have a second order phase transition. But as I bump it up, there's a first order phase transition. As I bump up the amount of response to.
Is that graph asymptotic on the right? Or is that actually become a straight line? Because I'm curious what the significance of it is.
Yeah. Effectively, what happens when you bump up there is that, what you'll see with the density of state is it just becomes impossible to have any paramagnetic like phase transitions. Superfluidity goes away. So there's like a hard wall. And in fact, 0.5 itself doesn't actually have any phase transition. It's fun. It's interesting.
So it's just in a single phase.
Yeah.
Period.
So, I want to show you, obviously. So, and here the little inlet is just a zoom in of like basically where this little dot is. Or wait, no, not this little dot. From here to here. Yeah. Right. From 0.46 to 0.49 is showing, okay, like this little bit of evidence where microcanonical ensemble and canonical ensemble disagree shows us that we have first order phase transition, yada, yada. It's just like, okay, I don't know how to interpret this with the method that we have, but hey, I don't have to worry about it because we still capture it. We capture the fact that there's a difference between first and second order phase transition. That's all that matters. All right. So obviously I've talked about the phase diagram here, but when I showed you that picture of the phase diagram of water, it was a lot easier to visualize what the heck it actually meant because we could use the fact that everyone knows what water looks like in its different phases, right? So we're going to have to survive a little bit of extra math, but once we do that, I'm going to show you what this graph actually means. And I'm going to show you the peaks that I've been talking about with this concavity thing.
Sweet.
Yeah, it's going to be really fun. So.
Hey, Billy, can I get some more water?
And I thought this would be less than an hour.
Yo, right. You just can't stop talking once you start.
It's the worst. I'm just like, let's talk about the theory of everything real quick.
Yes.
While I get into phase transitions. You're right.
Ease gradually.
Let's sky high and then be like, no, here's this entirely different thing, and it's science. It's great.
So you are going to explain this puppy, right?
Absolutely. In fact, we are about to build that structure up.
Oh, cool.
So, mathematically, I have told you that everything we're doing be great. Everything that I've done in this field means that all we have to do is look at how to count the different possible configurations of your system. And if you can do that, you can get the density of states and you can get exactly your phase transition curvature stuff. Well, we're about to do that. So, remember how I told you about the two easy ways to classify this model? Is that if I, of course, three things, excuse me, but one of them doesn't change. The number of atoms in your system, the number of spin sites you have, how many of those are plus or minus one, how many of those actually have an orientation, and then how many of those are spin up, right? And if I tell you those three things, I can not only fully determine the energy, but I can also count those. So in order to talk about this, we're going to have to talk about a fancy mathematical function called the choose function. Yes. If you've ever done anything in combinatorics, you've run into this. Combinatorics is the math of counting. It is where we find the question of how do I count, every prime number, or how do I count,
How do I explode any simple equation into an enormous mess? I choose.
Yes, it's so beautiful. What I find absolutely fantastic about this is that this project is literally made for my undergraduate like schooling because I took so many classes. Uh, there were a couple of professors in undergraduate in the math
Not
department.
there. Oh
Can I get one of those, please?
yeah. Yeah, bring some. Put them in actual whiskey glasses.
I'll drink that on camera. It's fine. I'm an adult. So I had obviously, you go through professors and you have your favorites. I liked like the entire math department at USF is top notch. Let me tell you, great people. But there were two that I really liked. Well, a few, several that I really liked, but two of them I took at least 3 courses with each, 3 or 4. Actually, the other one I took 4. 3 courses I took with Professor Brendan Nagel, the combinatorics guy at USF. And for context, anything beyond a general course, having more than 2 of is like a lot. So 2 is like you're actually really interested in this thing. Oh, should I write names?
No. In case you need it.
Oh no. We're gonna be fine.
Good.
This is all.
What, you don't want to do your choose by hand?
No, I'm not gonna do choose by hand.
Damn it.
I have the equation here, but I'm gonna describe it and then show what it looks like.
Okay.
But we'll get there. So, Brendan Nagel, combinatorics. Took 3 classes with him, which is 3 specifically on that, on how combinatorics works and the notion of figuring out graph theory and basically how to count fancy things. Fantastic class, fantastic gentleman.
We do take 3 calculus classes.
We do, but that's a general subject that like is so fundamental. You have to. Now, if you really like calculus, you do go beyond that.
Right.
You go into vector calculus. Not everyone takes that. You go into differential geometry. Not everyone takes that. You go into higher dimensional stuff. So,
But who took this? This
so
guy.
combinatorics, its own separate field of mathematics, its own whole like lane and number theory. Well, not number theory, but like number theory kind of pops into it. But like combinatorics is its own thing. It's got some really interesting problems, and it's a really difficult subject because counting selectively is really hard. In addition, differential geometry, very different thing. It's like,
Oh, this is what you meant earlier when you were saying counting selectively is hard. Because I'm like, how hard is it, even though it's an infinite amount of time, to count the multiples of 7?
yeah. No. It's hard to know that you are counting the correct things.
Right.
Right. And yeah. So and then in addition, and so counting it's like a discrete structure set, right? There's one thing, or there's 2 things, or there's 3 things. There's these individual jumps. There's not a smooth transition between having one, say, 1 apple and 2 apples or something, right?
That's tough.
But if you do want that, yes, please. Yeah, I'll take a glass of that. If you do,
It's actually sweeter than Jack.
perfect. Yeah.
I mean, Jack always smells the best. Nothing smells as good as Jack.
Oh my God, no.
We might need more coasters. Now that I'm thinking about it.
We'll see. Anyways, but there are some times when discrete counting structures absolutely don't matter. And in fact, you and your wife, man. There are times where, it's important to be like, no, okay, we got these discrete counting structures. Everything that I care about comes in these nice, neat packages, and I don't have to worry about how things change around. But when I do have to worry about these smooth transitions, I've got calculus, right? The fundamentals that we have is pretending that, the discrete structure of atoms is fine enough that it is in fact smooth, and then we do mathematics, we do calculus on that, and then pretend,
Thank you.
everything's fine. But if you want to worry about that contiguous behavior, then it requires a whole different set of mathematics. And usually, you kind of go into one field and you only study one type versus, the discrete versus the continuous. And this is just like, no, in fact, here's a field where you need both of those structures. You need to be able to do these discrete counting structures. And in addition to that, you need to understand how that structure that you've built up actually flows and moves, even when we make a more continuous approximation of it. It's like, yeah, this is literally what my undergrad was built out, because I spent 4 classes doing geometry, and I spent 3 or so doing graph theory and combinatorial studies.
Didn't you also do you did what is it called, geometric calculus?
Yeah, differential geometry.
Differential geometry, right?
Mm-hmm. Which is the geometry of changing stuff. It is the mathematical basis of general relativity. Aptly named Christoffel symbols form all of the math of general relativity. They are awful. Never do them.
We'll be doing them soon.
Why? Yeah, gonna learn how to make gravitational waves and predict those, but that's gonna be cool. Anyways, so the choose function, right? Combinatorial object. How do we select?
I've been trying to avoid it.
I know you're distracting me, and I'm like, I'll let you, but here we go.
Let's do it.
The math begins. So, what is a choose function? Well, it's a fancy
Pull one up so people can see the
bunch of parentheses. No. I'll just cut to the chase, and we'll just pick up, in fact, the density of states for the BEG, and then we'll kind of explain it. So, the density of states,
there it is.
The BEG model is this. And that's a lot of gobbledygook. So let's explain what it actually means. Right. So a choose function is this set of parentheses here. And what is it? Well, it's the answer to, if I want to get creative, how many ways can I go to Domino's? And how many different unique pizzas can I create? That's what it tells you. So Domino's obviously offers some amount of toppings that you could have. And let's say it's 19. You could just have plain cheese pizza. You could have the different
Calling
cheeses.
It pizza is a little bit of a stretch, but we'll let it slide. It's a spherical cow.
Pick your favorite pizza place. They work the same.
Anyhow. Excuse
me while I try to broaden our appeal past
spherical cow.
0.002%. So right, like
Domino's is not a choice; it's a lack of options.
I mean, fair, but like, okay, like let's say in some absurd world, you consider making different types of pizzas a creative outlet, and you're interested how creative could I possibly be? So, if I, and obviously, right, like I could. If let's say the options are simple. You've got pepperoni, you got sausage, you got peppers and mushrooms. Easy. How many pizzas could I make out of that? Well, I could easily
pineapples.
I mean, I do in fact love me some pineapple pizza. Yes, I'm all right with the hate from that. Look, human imperialism brought about many terrible things, but it did let us put on fruits from opposite sides of the world onto the same beautiful little flat
pie. That's a good point.
Right. Worth it. 4 options. So obviously, pretty easy thing, right? I could say, and let's say you're not allowed to choose. I mean, if I can make 4 pizzas from that, right? Very easily. I could say I can have a pepperoni pizza, I can have a sausage pizza, I can have a peppers pizza, I can have a mushroom pizza. But then you start mixing them, right? I could say, well, I could have a peppers and sausage pizza, or I could have all 4, right? How do I count the number of unique ways that I could do it? Because what's not going to be interesting is, well, what if I have a pepperoni pizza, or a pepperoni pizza? For the sake of not sounding silly, we're going to assume that that's not possible. You can choose. You can say either there are pepperonis on it or not. Right, a binary choice.
Okay.
Right. We're not going to let you make a stack of.
Otherwise, this choose function would be much more complicated.
Yeah, we're going to start with the assumption that, hey, you either can have an ingredient or you can't. But
Now, some of this is in physics is dictated anyways by like Pauli exclusion and things like that.
yeah, absolutely.
Yeah.
But here's an important thing. If I have say, okay, call them up and I say, okay, I want a pizza with pepperoni and sausage on it. That's one pizza choice, right?
Mhm.
If I call up my lack of choice store Domino's and say, I want a pizza and I want sausage and pepperoni on it, have I made anything different? No. Because even though I've changed the order of pepperoni or sausage where that shows up, I haven't created a new pizza. It's the same type of pizza.
Although I'd argue somebody like me, the order that you put that in might actually affect the way it tastes. But I get what you're saying. Yeah.
Yeah, sure. I mean, all right, you could potentially have layering and stuff, but that's like a 19th order term in your Taylor function. Come on.
Yeah.
It's way out there.
My pickiness is not quantifiable.
Doesn't matter here.
Yeah.
So and excluding that redundancy is an important thing. And that is what your choose function does for you. It lets you know how many unique combinations you could have, right? If I care about ordering, it's something called a permutation. But if I care just about whether it's present or not, it's a combination. So the density of states for the BEG, for this superfluid helium transition, cares about three things. And there are going to be two sets of combinations that matter. First off, what's most important is I want to know, out of the atoms that I have, how many of them are going to have a sign, are going to have an orientation to them. That's what this first term here is going to represent. That's what K is going to represent. K will represent the number of atoms in your model that are either oriented up or oriented down. Effectively, what K, I should remember how this actually works. So it's left. K represents for me the result of this summation.
Mm-hmm.
Okay, it's just, okay. How many is the total numbers of atoms that I have in here that either are up or down? Summing over that gives me that object.
Because there'll be one, whether it's -1 or 1.
Right.
Right.
Because the power of multiplying negative twice. Right. And so the number of configurations that I could have, if where you have it set up in a line of like, okay, there are 50 atom slots, right? The number of configurations that I could have where say 3 of the 50 atoms present have a spin up or spin down, that's going to be told to me by this mathematical object here, right? And then because the model is what's called infinite range, which is basically the fancy way of saying each atom interacts with each other atom equally, right? That idea of the Bose-Einstein Condensate, the atoms spreading out so that all of them are everywhere all at once. This is often called long range or infinite range interaction, right? The space away, since you can reach infinitely far away, it doesn't matter how far away you are, you affect them all the same. Which is different than something like saying that electromagnetism is an infinite range force, but yeah. Technically, and gravity. Like technically, you and I feel the gravity of the Andromeda galaxy. But because it depends on distance,
it's trivial,
right? That's different than the infinite range interactions in this model.
Right.
But
yeah, well, because you're implying that the effect has an infinite range.
Right.
Yeah.
Right. And then next I want to know, well, okay, of those possible configurations that I considered where I said, okay, these are, 3 of the 50 have some orientation. Well, then obviously the next thing is, well, what are the possible configurations of those orientations? And that is what this guy is. Of those particles, those atoms that have an orientation, how many of them are oriented up? Now, we can classify this in terms of the basically the overall magnetization of the system, right? Because I know the overall magnetization is the number of up minus the number of down. And this will be the overall number of up plus the number of down. So the two downs will cancel, and you'll get 2 times the number of up divided by 2, giving you the total number of up-oriented ones. Just so that I don't have to like...
Matrix.
Yeah. So I don't have to like write it out step by step by step by step, right? Okay. Because here, this is determined fully by knowing basically the overall magnetization of the system and the total... Let me call it a quadrature. And why is that interesting and useful? Well, because it goes back to the Hamiltonian. Oh, I have disappeared. My guy. No. Oh, Windows snapped it to the other screen. What a dumb thing. Right. Now, so frustrating. Why is this interesting? Well, because in my Hamiltonian, M, the overall magnetization, is this other sum.
Mm-hmm.
So I can characterize my energy by knowing the values of these two sums. So when I do my density of states, hey, I can characterize it in the result of those two sums. Hooray.
Right.
Now, obviously, it's really hard to look at a massive atoms and go, how many of you are spin 1? Right? Really hard to like be like, tell me how many of you are spin 1, please. Please, I really want to know, right? Hard to do that. Instead, it's much easier to put it in terms of what is the energy of your system? Because I can map that to a temperature that I should read from a temperature gauge or anything else, right? I have physical apparatus that measure that much easier than I have for going, yeah, but how many of you are spin up?
Right, and from that graph you showed before, we could tell that. But the amount of energy we put in and then the resulting temperature is going to be based on that ratio.
So it's much more natural to talk about temperature and energy than it is to talk about number of spin 1, spin up, spin down particles.
Right.
So using the Hamiltonian, we get the second set. And basically, all I've done is said, okay, and actually followed this paper here. Said, oh, okay, this is K, and this is M. Well, let me just solve for K. And then replace K with a function that is a function of energy, H, M, and these, delta and J's. And so that's the much more, natural way that I would talk about it, because that's what I can measure. Okay. So what type of shape does that give me? Well, it gives me this shape.
Now, what are the limits here when we map this? Like, what are we iterating over to get this?
So what you're mapping, which actually, no. You know what? Why am I showing this again? I don't need to show this again. I will show you. Nope. There we go. Looks like that. And in fact, let me show you what the top-down picture looks like. Much better one. Let's go this guy.
Looks like a part in Kerbal Space Program.
Yeah, it's great. So here, this is what we create with that. What we are... Oh, these limits are all off. G. Here we go. Let's not use this one then. This is what you get when you like, hey boss, let me show you quick graphs and then not worry about the limits. All right, so this is I've changed the delta on you a little bit, so the shape has changed a little bit.
Okay.
And that's actually going to be an important point for what happens. So what do we got? Well, we have this shape, and it, so what we have the possible energies that you can experience along this axis here, right? So interestingly enough, as you change the value of delta, right? If delta becomes increasingly small, there was a minus sign in front of that J in the Hamiltonian, if you noticed. And what that means is that it's possible to have a shape that just reaches into what we would define as negative energy at that point. Now, obviously, that's
warp drive.
Not quite. It's negative energy in the sense of where you set your starting point. Right. In the same way that if I, set this as my 0 point for gravitational energy, well, then down on the floor is technically negative energy. I haven't made negative mass yet. I know. I'm sorry. Audience will get to that talk at one point.
2021 we'll do that.
Heck yeah. Warp drive requires negative mass. What does that mean? I don't know, and no one else does either. Yeah. But so what we have, and then we have the energy that you can have possible, and
now I gotta ask, is that point actually on 0.3?
I'm bad at Python. I figured out how to do it later.
Okay. All right. This is supposed to actually be symmetrical.
Yes, this is in fact symmetric.
Okay.
As evidenced by that choose function, those parentheses are symmetric. There's nothing you can do to get away from the fact that they're symmetric. Yeah. I don't. We're flying by the seat of our pants here, bud. So this is what the density of states looks like effectively. As I go to, 0, the highest point, right? Just like this shape here, the most number of states available is where I have, a high amount of energy and no magnetization. As I push magnetization, the number of configurations that I can possibly get, right, decreases. If I go from the center line down here, it slopes down real quickly. Okay. There is a possibility here where I can have energy, right, states where I have no magnetization, but still some amount of energy. But, well, okay, so this is what the general shape of the density of states looks like. But what is it that we're actually trying to capture when we're talking about phase transitions? Do you remember?
Well, if I remember correctly, it would be basically where these two surfaces meet right here.
You have remembered what indicates a phase transition. But how did I know what a phase transition was to begin with? Or a phase coexistence, perhaps, is better. Do you remember?
Well, you were looking at the derivative.
Mm-hmm. So the curvature tells you where they should approach. But the thing that tells you when a phase coexistence actually occurs, right, that you would look at and say, oh, a phase coexistence is here, is not that. It's not directly the curvature. The curvature tells you where it will appear. But the thing that lets you look at it and go, oh,
is this where, like, how I can tell that water's not frozen?
Right. Or, like,
what is the physical characteristic of that?
The physical characteristic of this glass of whiskey or bourbon.
Okay.
Right?
So you told me superfluidity what occurred at... Well, actually, no. I'm not sure.
So what you will look at is like, okay, here's how you do it. Pick a random atom from this glass in my hand, right? Well, from the glass of the system that I have, not the glass itself, but what the contents of the glass, right? What is it?
Whiskey.
Is it?
Oh, okay. So it's some atoms.
So you could pull a whiskey atom, but what else could you pull?
Or whiskey molecule, but yeah.
Yeah. You could pull a thing of whiskey, but what else could you pull?
Air.
The water.
Oh, the water. Okay.
Right?
I mean,
so we'll look.
Whiskey is mostly water.
But that's the point. There's a difference between the two. Let's just say it is water in my hand, right?
Okay.
You pull an atom from here, you don't know whether the atom will be from the liquid water or the solid water. And that's
you mean just randomly, not me looking with my eyeballs.
I mean, yeah. If I literally pick it out.
Okay.
Right.
Okay.
But if I just sample a random atom from that glass,
I see.
What I have is, and that situation isn't described by the density of states, it's described by the probability function, right? your probability of selecting a molecule of water that has the properties of liquid. Or,
Is this where we're getting back to counting functions?
So the density of states is the bit counting function. The probability, if you remember,
or partition function.
Yeah, kind of. Because what you add on to this density of states is that, if you remember, right, to construct the probability, that I don't have, is that I take the density of states and I divide it by the partition function and multiply by an exponential function that takes the variables that the density of states and the partition function both care about.
Okay.
So to really get a qualitative feel of the probability function, what you want to look at is for a certain beta, you can just look at the density of states times that exponential function, which I'm about to show you.
Ooh.
Yeah, and that's so. What happens is we have a split, and that's when we know phase coexistence occurs. There's a bimodal peak or a split in the peaks of the distribution. Right. If I look at this glass of water, right, if I pick a random molecule from here, what will you get?
Trick question, or is it water again?
No, it's liquid water.
Okay.
But you'll always get it.
Right.
The distribution is tightly bound around that average. But here, I will get either liquid water or solid water.
Okay.
But the average of the combination is actually between the two. And it's that understanding of like the distribution splits.
So let's re-answer the question that you asked me then.
Mm-hmm.
So you're telling me that the physical manifestation of the phase transition here is the fact that if I randomly sample, I'll get things on this side or on this side?
So, depending on your environmental conditions, right? So, right, the what I have here, what is this in equilibrium with? It's in equilibrium with the temperature of the air around it. That
Maybe not,
thermostat
but
control.
Yeah.
Right. Yeah. Right. But that's how I have control over this, is I can touch it and change the temperature of this
Right.
glass, and I can cause it to melt faster. I can set where the average energy of that system should be. Well, what do I want to do? Let's do the low D first. So if I take this is such a small picture. So I have that density of states. I have a relatively low delta. This is 0.3. And I've set my temperature here equal to 1. So this is a relatively high temperature. By setting these two factors, the mixture of the helium and helium-3, helium-4, I get this shape. And then basically I'm saying, okay, I have forced this system into having no magnetization by having no field. So on average, we should be along this magnetization equals 0 line, right? The peak should appear across that.
The 0.3 line?
Yeah. No. Yes. Boy, do I need better friends. Who make me show them the slides beforehand instead of letting me whirlwind and be like, let me just talk about this.
No, this is
pictures,
great.
Pictures.
This is great. I'm sure anybody that has ever made a graph is like, oh, God.
Oh, Matplotlib, it does some dumb stuff sometimes.
Yeah.
Anyways, so I force my system to have 0 magnetization overall, and I've also set the temperature so that its peak is around here, right? So the average energy is right about here, but obviously if when I sample this, there's a probability that I'll get a sample. There's a probability that I'll get a sample that is, a little bit less energy than what the average should be, or a little bit more energy than what the average should be.
Mhm.
A little bit more magnetization or less magnetization than what I would have the system average be, or the ensemble average be. Any particular system that I select from there, or any particular configuration that would lead to, this energy, this magnetization, has some probability. Now, if I get really far out, well, okay, it's really unlikely that I'll select a system that has this energy and this magnetization. But it's most likely that I'll get this energy, this magnetization.
Is there an actual value assign to that purple in terms of probability?
Ooh, I mean, yes, off the top of my head, I don't have it. So,
But it's vanishingly small.
yeah.
Okay.
This is close to 0.
Okay.
Effectively.
And there's no gradient that I can't see here in that purple.
Yeah, no. We go from red down to blue, violet, and then
So there is a
lowest.
gradient implied in this purple section as well. It's just
No,
so
not in the
vanishingly
purple
small.
section. Just
Okay.
just here.
Okay.
Basically, here the purple will consider as the lowest possible value.
Okay.
So 0
Epsilon.
effectively. Yeah.
Okay.
So the method that I have control over is the mixture and the mixture of the two isotopes and the temperature.
Mm-hmm.
And the thing that right now that I'm going to play with is the temperature. Right? If I decrease the temperature, and actually if I do this that way, it's going to do that. I'm just going to drag these over. If I decrease the temperature so that the average energy is about here, notice what happens. I don't have a peak in the center.
You have 2 peaks.
It spreads out. This is a second order phase transition.
Now, all second order phase transitions have what I'm calling 2 peaks.
Yeah, you'll have. It's not the number of peaks that makes the thing. It's that if I pull back my temperature, right, these peaks will smoothly transition into each other, and they'll always be at the same distance along in the energy direction. So basically,
So once you go from 1 to n number of peaks or whatever, or most common scenarios, that it's a second order.
no, that potentially would be a first order. But there's for this particular system, yes, there's extra features about that shows up, and we'll get into it. It's that appearance of that latent heat I was talking about, and I'll show you what that means in a second.
Okay.
So, and then obviously as see, this is why it jumps over, and this is annoying. But if I increase the temperature even more, right? No longer are they even slightly attached. They're just like fully separate, right? The energy forces me to have to sample from here to here. And if we look at this model, that's basically, right? I've put my energy so that, it's here. It should be along about 0.5. So that would put it at 0 magnetization. Oh, here. Well, the system isn't even supported there, right? So the curvature.
The system isn't supported.
Yeah, like there are no realizations.
Okay.
Of
and that's what you mean by
model.
The system isn't supported.
Yeah.
Okay.
Yeah. There's no mathematical support there.
Okay.
There are no values of energy and magnetization that have realizations that are actually this value where my mouse is, right here. Right. So instead, the system being forced into averaging there samples from things around, right? And the curvature of the density of states, if I look at, this thing here, the curvature here will show it, or should show it. We'll get into some interesting bits here.
Oh, this isn't interesting.
Oh, no, this is not interesting at all.
That's why we're talking about it.
Absolutely. Now, that's if I change temperature. Well, if you remember the phase diagram, right, I had 2 axes. You had temperature sliding around, and when the temperature was decreased enough, I know that it should show me a phase transition, phase coexistence, which is exactly this, right? But I also, had that other direction. I had that delta direction, and as I changed delta, I shifted from second order phase transitions into first order phase transitions. What does that look like here? Well, I'll show you. And basically, by doing the same processes, if I can just have my brain remember how mice work. And that's done very simply here. I have increased my delta, and actually, we'll get that. I'm actually going to change delta.
The shape keeps changing. I know I asked this, but just to reiterate, the purple doesn't mean 0. 0 is the white.
Mm-hmm.
The purple means that This is the smallest possible chance.
Yeah.
But it's not zero.
Well, yes.
Okay.
Right, because effectively, so the white tells you that the density of states itself says, oh, okay, it's 0, right? Anywhere there was purple is a spot where the density of states is not 0. But it's multiplied by an exponential factor, by an exponent e to the negative something.
Mm.
And so as I get away, right, that negative value gets really, really big. And when you get to this purple, effectively, it is so big as to be 0, but it's not 0 because of the density of states. It's 0 because of that exponential decay. But technically, right, e to the negative x is not 0 until x is equal to infinity. Right? I have to have a infinite value in e for it to truly be 0. It's always a little bit.
Right.
Little tiny bit that you could never see and not distinguish from 0 past, like 3, basically.
But at some point, I mean, if we run an experiment enough times, will you ever get a result in the purple? No. Okay.
At that point, it is so small as it's below machine precision.
So basically, like the chance that I'm sitting in Jupiter's core right now, I'm just phasing in every time I say a word to you.
Mm-hmm.
Experimentally, it's never going to determine that, even though if you were to draw the graph, that might be in the purple.
Right.
Okay.
Right. So I've changed delta, and actually watchers will watch that as I do this. I changed delta again, but it's fine. It's pretty close. This is a value that's past that tri-critical point, and that's what matters. Here I have the high temperature limit, so I've got a nice core. If I shift it down, send my temperature all the way down to there so that the average energy is here, what you'll notice is that it starts to bend along here.
Yeah, you can see some blue all the way in the curve.
If I push it down even further, watch what happens.
But there's little peaks over there in the...
Yeah. This is that splitting, right? I still have a core, but I have a wing that pops here and here. But what's interesting is, well, notice this core here is about there. If I go up to get to the top, I have to shift along the energy. So the peaks here and here are at a different energy than this middle peak here. That's what we think can be interpreted as a latent energy that pops up. That...
Well, I mean, isn't technically the presence of a B field kind of a latent...
But you don't have... This is still at overall magnetization equals 0.
Oh.
This entire time, the B field has been 0. There is no B field, right?
Okay.
If you had a B field, you wouldn't have this splitting here, because the system would go, oh, the B field's in that direction or in this direction, and you would have that peak and none of that peak, right? You would have, if the B field was negative, you would have this peak only and none of this peak.
Oh, right, because you wouldn't have the presence of both fields at the same time.
Right.
I see.
It's
okay.
the fact that we have no field, so the system has to, the ensemble, the system has to, on average, have 0 B field, have 0 magnetization response. Okay. But the too low energy forces it to sample from different configurations, right? From vastly different configurations at the same time. And that's a different phenomena from this peak being laterally different. That's this first order phase transition that pops up. That's really cool. So I've shown you how, the phase transition, the phase coexistence shows up on your density of states when you look at the probability density function, right? And how it physically, shows the process that we're expecting. Shows if you take this picture, right, and I fiddle with beta and delta, again and again, the thing that I get, right, if I ask, when I look at this picture, does it have 2 peaks, or does it have the three peak latent structure? Yes or no, yes or no. I can construct the phase diagram that bar have. But me showing you these pictures That's not the concavity method that I talked about, right? I haven't talked about derivatives or concavity at all. I've just said, hey, look, this is what your probability distribution looks like.
You've got multiple local maxima.
Right. And basically it's like, oh, okay, I expected this behavior. If I look at the probability distribution, oh, okay, it's in fact there. But that has nothing to do, we haven't at all talked about the density of states concavity. We haven't talked about how it's geometry at all. Right? We've simply said, okay, here's the density of states, so I can tell which configurations could possibly be supported. And then I slap on the exponential to look at, okay, well, based on the environmental conditions, what does the system actually do? But now we got to show, well, how does this actually work? Right? How does concavity method work to potentially produce that graph that I showed you before with the 3 colors? Right? Well, to do that, let's again briefly talk about the equation that we had. Right. Man, I'm just going to keep popping these open. Right. So the way that you would deal with this is, as I had done with all my other models, right? We constructed something called the Hessian matrix, the stability. It's effectively, I look at this thing, I take the log of it, and then, which that adds a little bit extra mathematical complexity, but I basically want to construct 4 different quantities. I want to take the derivative of the log of this with respect to the energy and the magnetization, because I want to look at the curvature of this equation in the space of the density of states, right?
Hey, Billy, make sure you stab him. Totally out of context.
Oh, dear.
Marinating steak. Yeah. Give him the good stabby first.
Right. Because, I mean, you always were, Billy. It's fine.
The audience doesn't need to know whether they're live or dead.
So, right, the promise of this model was, okay, look at the concavity of this structure, right, the log concavity of this structure, and based on the results of it, I can tell you where phase transitions occur. So how do we do that? Well, first we need to take the log of this thing, but to get the concavity, I simply need to construct the all possible combinations of second order differentials of E and M, energy and magnetization. So what is that going to look like? Oh my.
I thought the choose explosion was bad.
I know. So, where's my mouse? Fumbling here. Let me pull this back. A little relief. I'll actually pull up the documentation real quick. It's pretty simple, right? So I want to take a derivative with respect to one of these variables, energy, and then I want to take the derivative with respect to it again, right? That is a second order derivative, right? Since I'm dealing with multiple dimensions, I can take derivatives with respect to energy or with respect to magnetization, right? That is another derivative that I could have. Effectively, what I want to create is this guy here, right? The S is, I've defined as the log of the density of states. And I have 2 derivatives with respect to magnetization, a derivative with respect to magnetization, and the, well, here, this I'm calling 2-star. This is a different model, but the structure is still the same. Right? It would be E and M instead of M and S.
Okay.
Right, but this is kind of what it's going to look like. And this object is basically looking at the function going, oh, okay, well, what's the 3D parabola that emanates from a point? Is it going to be like this? Is it going to be like this? Or is it going to be one down, one up? Right, like a little saddle. Effectively, that's what this thing will tell you. And the way that it most effectively tells you is that you look at its eigenvalues, if you remember those.
Oh, yeah.
Right. So the eigenvalues, like what we said, basically define the, God, how mathy do I want to get? I don't want to get that mathy. The eigenvalues are basically ways that you characterize you can characterize the type of transformation, the type of thing that matrix, that derivative change is through its eigenvalues. Here, this matrix tells you if it's down, then both of its eigenvalues, because this is a two-dimensional, right? 2 by 2, so it has two eigenvalues. If both of them are negative, concave down. If both of them are, either of them are positive, not concave down. So what we're looking for here is we take these derivatives, and if the function, the density of states, right, this guy, is concave down at that point, which actually, let me get rid of these, and let's go back to, instead of the probabilities, let's look at, again, the density of states, right, the actual function itself, right? So what I want to do is say, like, at this point, okay, here, I would ask, is it concave down here? Locally, does it look like this, or does it look like that? And if it looks like this, if it looks down, looks nice and convex, everything's all
concave down from what we're calling the apex.
Yeah.
Okay.
Well, not even the apex.
Or the center point, or
it doesn't have to be, in this case, relative to anything other than the point you're asking about. I say, at this point, does it look more like a downward parabola or more like an upward parabola?
Okay.
Right. Obviously, where you are on the parabola will make it look different, but it'll still look like an upward parabola whether I'm at this point or at this point, right?
Yeah.
If the parabola is that, right? So, if it's concave down at that point, we say, I say, hey, there's no phase coexistence that will occur if my system average, right, is at that point, right? So if I set my system so that that little bubble should be around that point that I'm asking about, and at that point that I'm asking about is concave down,
now
I know the overall shape of that distribution will be tightly bound around the average.
Okay. Now, is it easy for you to know in advance what you have to set your parameters to get that point be where the average is?
Oh, no.
Okay.
I mean, sort of.
All right.
Sort of. So in order to...
So just a very light layer of water and salt. Yeah. We're out of soy? Sorry.
Oh, we're almost... No, that's fine. We're almost getting there.
Oh, really? We're not there?
We're basically there. We're wrapping up here.
I'm kidding.
I'm just...
Take as much time as you need.
100% surprised. But, these conversations are always fun, isn't it? All right.
It's the nature of this work, man.
You think you can explain a thing in 5 minutes to grandma, and then you're like, oh, no, I know nothing. This takes a little bit of work. I know a lot, and then, oh, wait, it just takes so much to actually talk about it.
Background and context, man.
Hey, I mean, the source of half of our political problems these days.
That's why you really can't fail the first 2 years of undergrad physics and then pass the remaining 2. Because you just don't have the background. Well, I mean, unless you somehow rush right through the first week of rehash.
Yeah, yes and no. I mean, you can lack intuition for like some of the basic stuff. I mean, undergraduate physics, they're really like throwing.
So you're telling me that you're going to do classical mechanics with no calculus?
No. They don't teach you calculus in physics 1 and 2.
No, the first 2 years of undergrad in a physics degree.
Oh,
it's going to be calculus and all that stuff.
Fair enough.
Yeah. It's like, okay, come on.
Yeah. I mean, hey, embarrassingly, I had to be told to take derivatives of like physical structure equations. I'm like, wait, what? You can take derivatives with respect to different things. Like, I was a very smart but very dumb undergrad when I first started doing research.
It's me a while.
Weird phase transition, man.
Because I started it as an adult, because I rejected, like, when I was in high school, I was like, no, I'm just going to sit here and read C programming language reference guides and things like that. I completely ignored it. So when I got to college, it was definitely an interesting experience. And it was a while before I even understood the basics of calculus. Like, what I mean, I could regurgitate the rules very quickly, but I didn't truly understand. Oh, I was working with infinitesimals. Like it took a little while before that actual fact clicked.
I mean, I think I've talked to you about this, about how, when you take a course on something, they really like, right? And I've talked to many people about like this in the nature of the podcast. Right? Like when you take a formal course on something, they really go into like, all right, so like let's say you got a car, you got 132 nut bolts, and like each of them look like this. Like you literally look at each individual part, and the structure of formal academic classes is that you go through the itinerary and like you learn about each nut, each bolt, each part, the steering wheel, the crankshaft, the axle, and it's kind of left up to you to realize, oh, I'm looking at this means car,
Right? Oh, this is
Like-
this is suspension. Yeah.
like, oh, this serves this piece. This is what this means. And like, it's so, I really do love the structure of like formal math language. It has such a beauty of like really specifying exactly what you're talking about. But also, you do have to spend 5 minutes after you look at a theorem and the statement that's made and go, yeah, but what does that mean? And not like in a philosophical way of just like a BS philosophical way of like, yeah, but what does meaning mean? Which, to be fair, is an important question. But like you have to just digest what has been said to you and like what are you saying before it can even make any remote sense in your brain. You can understand what's going on. So it's a fun way. I really like how it's structured because it's its own little programmatic language, but it is definitely not intuitive, and it takes a lot of wrangling because it's something so different from what your brain naturally wants to do. It's great.
And speaking about what are you saying?
So, right? Because actually, you know what? They're not entirely put up here, but let's actually do that. So, what I would actually say is let us look at these two pictures here at the same time. My God, we have the technology.
We do. We have the resolution.
All right.
I wonder how bad that's going to moray.
Oh, it's
Well, actually, it won't moray because it's going to be a little
it'll be great.
out of focus.
So, right, what I've been saying this whole time is we work on two different objects. What I'm saying is that I look at this object because when I look at this object, I know what this is going to look like. So, what I do is I say, okay, let me say my system, my environmental parameters, the things that I have control over, the temperature, the magnetic field, I set them so that my so that my system average will be right here where my mouse is.
And you said that it's not always intuitively obvious how to do that.
Right.
You got to kind of screw around with it a little bit.
We'll get to that, and actually, it shows up a little bit in the picture that I showed you. But we'll get there. And what I ask is, okay, at that point, are you log concave? If the answer is yes, I go, well, the distribution at that point will be centered around the average. So if I look at the shape of my probability function, I know the peak will be right on that average, and everything that I have will be really close to it. And what do I see? When I look at my probability function over here, I go, aha, I have set my thing so the average is there, and look at the distribution. It's all nice, well coalesced around that point. So if I sample from it, I might not get a system, a configuration that has the property of the average. I will get something, say, up here when I sample, or something down here, but it will be close to the average properties that I've set. Right, it'll be
at least in character.
Yeah, it'll be.
Right.
It'll still have the same flavor, feel. It'll look a little bit different, right? There's
The bottom of Mount Everest is still a mountain.
Right. There's a little bit of like, oh, I'm a little surprised about what it actually looks like. And like if I look at this table and actually, zoom into the atomic structure, I might be surprised, but it's still gonna look like a table. Aha, right? But what happens if I set myself over to here? Well, from this contour plot, I can clearly see that locally this is not log concave. So I've forced my system average about here. Well, what happens to the density, to the probability function? when
Now,
I go
how is
there?
that obviously not log concave?
Oh, because if I, right here, it's bowing out. So basically, if I take this point and this point, the line connecting them, the closest line connecting them, right? Just a line.
Mm-hmm.
It goes out of this region.
It's a good thing you mentioned that because, and I asked that because I kept thinking log concave is as if I looking into the picture. I was thinking the slope around.
Yeah. Oh yeah. It's like if I took this and I oriented that way.
Okay.
Yes. Right. So this picture, the color kind of represents height, and the concavity is here most easily denoted by just looking at the shapes. So like this structure here, this would still be concave because the slice that it is still convex. Any 2 points I can connect with a line, and all the points along that line are within that shape. But if I go over here, and actually, we'll get into there. But here also, if I looked at this point and I said, okay, what's the curvature of this line, right? What's the second order derivative? It will clearly be out, and I would want it to be in. I would want it to look parabolic inward if it's log concave down, if it's concave down.
Okay.
Makes sense? Right? If I kind of look at the edges here, this point here, right?
That's definitely obscured.
That is definitely obscured. If I look at this point here, right, it's bending downward. If I look at this point here, right, it bends outward. And so that's the two different structures that you have. This would be like kind of up or out and versus down.
I might make you draw this.
Oof. We'll see. We don't need to go into, fortunately, too much more detail beyond that.
Okay.
But what I've been doing by looking at that Hessian matrix, right? Remember that 4x4 structure that I had, right? I can ask, okay.
2x2 or
2x2. Did I say 4x4?
Yeah.
Sorry. That 4 entry
okay
thing, right? I can look at the eigenvalues of that, whether they are positive or negative. Will tell me whether it looks like this or whether it looks like that. And based on, this is the wrong.
because we see both types of concavity in that graph. Depending on where you sample. Okay.
Right? Because I could either have, and actually perhaps this one is the better one to put up here, is that based on where I set my system average, right, based on whether I set the system average to here, which would look like this, or if I set my system average to here, which would more readily look like this, right? If I set my system average, well, here I've moved a little bit outside, but it's fine. It's the values I put. If I set my system average to here, right, to here, then what I'll find is I won't sample any graphs near where the average of my system is. I will sample things that are far away, either here or here, that on the whole average to here.
Right.
Right. But the fact that you have this different structure is exactly what gives you that phase transition, because you should have two different types of curvature. You should have, right, the picture of the paper. You should have stuff that doesn't have a phase transition fall into a phase transition, and then you have a split. That's exactly what we're expecting here. No split in your distribution, and then split.
So where is the tricritical point on that graph?
So the tricritical point, remember, exists not as a function along magnetization and energy, but as a point along temperature or energy and your delta function. So
okay.
remember what I was
So we
saying?
already picked. We picked it ahead of time, right?
So
right.
effectively what you're doing when I slide my temperature around, I'm sliding along this the magnetization equals 0 line here. I'm changing my energy. I'm effectively looking at slices
right
along here.
Right.
Yeah. And that's where this particular model gets a little trippy. right? It takes a little bit of time to figure out how do I do this. But fortunately, I can instead of having to look at this, I can just use my math. I have that thing. I can get the eigenvalues by looking at the trace and determinant of a 2x2 matrix, and that is actually a really easy mathematical process for it to do.
Mm-hmm.
And so I can say, oh, okay, take those derivatives that I need of this function, set m equals to 0, move along, take different values of delta, and move along my m equals 0 line, different values of energy, and ask, are you concave at that point? 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 Which is basically when I'm asking, are you concave at that point? What I do is I'm asking, okay, are the eigenvalues still negative? 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 And when I do that, what do we get? Well, let's leave that up. Oh, jeez. I'm making someone whose job it is to do actual presentations just die on the inside. It's beautiful.
Nah, dude, this is live.
Yeah. When I do that, the thing that I get is this beautiful shape here.
Oh, we're almost there.
Which you go, wait, what? Because my thing,
Is that actually how you spell quadruple?
yes.
Oh.
I know. Or at least according to Bar and every other source that I can.
Interesting. Okay.
Yeah. No text editor likes that spelling, but also no text editor likes quadruple.
Okay.
So, having changed, right? I'll look at this. I've got my different values of delta, the different mixtures, and my different energies, right? I've skipped over a little bit of math here about how to transform between, because the eigenvalues care about energy, but here we've got temperature.
But we can understand.
I've skipped over that. It's fine.
They're similar.
At this point, it doesn't matter that much. But I get this shape and I go, huh. My promise was that I would be able to tell you. So yellow here tells me that the eigenvalues have shifted positive, that at least one of them has gone positive.
Okay.
Which means there is some non-concave shape in there. And purple is that it is in fact concave.
Okay.
And so that would mean purple, right? This purple structure should correspond to here, right? This nice, beautiful behavior. And then the yellow should correspond to inside here. But wait. Huh. This line keeps going. This line swings underneath. Well, crap.
Oh, so it does actually extend beyond the bounds.
So, well, it depends on how you're mapping here. No, because this isn't actually the density of states. This is your phase diagram.
Okay.
Right. This is I've constructed by changing my delta to different values and then moving from high temperature down to low temperature, basically high energy down to low energy.
Right.
And at each point, asking along there, are the eigenvalues negative,
Right.
negative, 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 negative. And what this is telling me is that, okay, there's like, this is a slice kind of like this, right? 0.4 is what this picture here is for delta equals 0.4. So that means that it's about this line here. So there's a point where, as we go from high energy to low energy, I've got, okay, everything's concave, concave, concave. And then I hit a point and I go, oh, okay, look, right here, somewhere in between these two, right? The eigenvalue changes to positive because I can see from this that it's not log concave. But as I keep going down, it changes again. And in fact, as I shift from here, right? So basically lines that are shaped like parabolas to the left are not concave. Parabolas that are to the right are concave. What do I notice? This looks like it goes to the right again. This looks like it goes to the right again. These aren't
to the right or
opening this way.
Right.
Yeah. So the fact that it's opening to the right means that, wait a minute, this tells me, according to what I've described with the eigenvalues, that my distribution should in fact be tightly bound around an average again. Should be tightly bound around an average again, all the way down to here. My method has failed. Oh no. And this would be, a terrible thing to be like, I've put all of my investment into how um, how we can talk about phase transition, and it's all about concavity, and then to have it go, no, 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 this is actually in fact broken, and you can't predict things that we clearly know. Like we just walked through how it you know, 0.4, even that would be.
So what's the expected shape for that thing on the left then?
That the expected shape on the left, according to what I was telling you, should be this thing. It should give you this graph here, this line here.
Oh, okay.
Yeah,
okay.
yeah. These two are supposed to be the same thing.
Right. Because we divided out J, right?
Yes. That's why I don't have J here. I've said J equal to 0 because it's the same.
Okay. So clearly something's
amiss.
Yes.
Mm-hmm. And it does, in fact, because there's nothing wrong, it turns out, with what's happened here. Yes, this does change. The local concavity goes back to being concave instead of convex, instead of not concave. So what happens? Well, here's some little obscure bits of knowledge. Let's see if you remember. Do you remember in that talk when I talked about the conditions that were sufficient for concavity? I talked about the Hessian matrix. Do you remember anything else?
Not particularly.
There is an inequality, something called the Prekopel-Lindler inequality, that is effectively an inequality for...
I'm getting the word. Look.
It determines log concavity, but if I take the log of that inequality, it effectively becomes the definition of a convex function, which is basically, right, if I take 2 points in here and I connect them, let's say, God, do I want to go mathy? Yeah, I kind of do.
Well, I mean, we're about 2 hours in. Go for the math.
3.
Go. Let's do it.
All right, give me your iPad. Let's
math it up.
Let us see this. All right. So, how do I shift you over?
We slowly slip into oblivion.
I'm going to destroy your brains. All of them. Yes.
Meanwhile, everybody who's sober and watching this is like, oh my God, get to the point.
Oh, I'm sober as can be because I don't drink enough. Fair enough. Oh, this is so watered down at this point.
Actually, the water makes it a little sweeter.
It does. It does make it sweeter. All right. So how do we qualify a convex function? So it's pretty simple. If I had something, let's do this. So we have ourselves a X and a Y. And all right, my apologies for everyone who has flashbacks back to algebra.
I think we're beyond that.
I don't know what you're talking about.
I think we're well beyond that.
Right? The typical way that I would say, aha, I've got F equals to Y. So I would have some squiggly line here that I would say is in fact F.
Mm-hmm.
Right? And I'm going to split this into 2 different parts. Pretty simply. We're going to have parts that are concave and parts that are convex. And how do I tell that? Well, it's that the value of the function here, right, is always above the mean of the two. So no matter this part here, this yellow part is called concave because let's do here. This point I'll call x1. This point I'll call x2. Right? I can say that f of x is always
x1 plus x2 divided by 2?
Close. But I want to give it yes. Yeah. because you got to give it a little bit of a different thing. So the journey, right, going from x1 to x2 is going to be parameterized by a new thing, which I'm going to call delta. Actually, let me put it here. And delta is just going to go from 0 to 1. So that's what these brackets here indicate. It can take any value between 0 and 1. And so if delta is equal to 0, we're at x equals 1. And why am I calling it delta? Lambda. Lambda is equal to 0. We're here. If lambda is equal to 1, we're at x equals 2. And so the way that I can characterize this is by saying, it is x1 times 1 minus lambda plus lambda times x2, right? So that'll give me every value between x1 and x2, right? Based on the value of lambda being between 0 and 1, right? Okay. This value of the function, right, somewhere on this yellow curve will always be greater or equal to. You can make it strictly greater than or whatever, but that's mathy. Will always be greater than the value of this blue line here. That is just the straight line between, you know, f of x2 and f of x1, right? How do I make that line? Well, basic algebra, rise over run, right? We're going to go, okay, this is greater than
y equals mx plus b.
If x2 minus, but here's a thing that I can do. I can actually change that a little bit and put it in terms of a lambda, because I can talk about this point, not just the slope. I can talk about what point we're at along here. And if I do that little bit of extra algebra, what I find is that it ends up being, it's always greater than 1 minus lambda f of x1 plus lambda times f of x2. So the constants that are kind of inside here, choose a different color, that are inside here kind of pop out. And if it follows this inequality, then this function is concave. If it doesn't, right, the opposite, right, in the blue region here, the inequality is the opposite. It's always less than or greater, or less than or equal to, right?
Well, you've got an ambiguity there if they're both equal, right? What happens if it's equal?
Then it's a straight line.
So is it concave?
So it because it can be equal, you can have a thing that is a straight line is both concave and convex.
Okay.
Right? It's that straddling line between the two. And because that it's also kind of neither, it's like 0. Right? 0 is neither positive nor negative, but kind of both.
And for your case, all you're caring about is if it is concave.
Yeah.
Yeah.
Well, yeah. So I in fact care about concave. So it can be 0, and if it's 0, it's fine. Actually, it still has you coalescing to the point. It's only when it becomes positive in the eigenvalues. But this structure here, right, this inequality that I'm just describing to you is in fact has nothing to do with derivatives. I mean, you can derive this inequality from your derivatives, but it doesn't have anything to do with derivatives. And what's interesting is that, well, an interesting and subtle point. Derivatives give you information about something very specific. They give you information about local behavior, right? What does your function look like at that specific point? How does it curve at that point? And what it took a little while to realize, having played with this condition, is that it's not the local properties that are always determining things. It's instead some global properties, right? So let's see what that's going to look like. Just like how I was asking before when I went along the density of states, what we had to do is we had to ask ourselves, right? I set my energy and I went, okay, eigenvalues negative still, eigenvalues negative still, eigenvalues negative still, eigenvalues negative still, and I kept doing that, right? Instead of that, what I had to do to capture the Prekoppel-Lindler inequalities for log concavity, what you do is you say, okay, let's move along here and ask, is there a point, say, let's say I've set my average system to here. Is there a point of magnetization, if I go straight up or straight down, that has a higher value on the density of states? So this is a perfect example, right? Here, this is right where it starts to curve back again, right? So this is where the local concavity tells you, no, you should have no phase transition. But if I look, let's see, up straight about here, I get a different color. I get a higher level color. And that tells me, wait a minute. So even though locally it's fine, the system actually prefers, right? The density of states tells me it's much better, easier to make these states than it is to make these states. And that breaks the concavity not locally, but globally. And if I go through the process of asking, okay, change your delta functions, change, and then ask, okay, spread out from the m equals 0 line, does the density of states ever get bigger than what it should be as I go to the sides, right? Because, right, if I'm on this nice concave part, this center of the spline should be the most top piece, and then it slides off to the sides, right?
Okay.
If I'm up here, and then it slides off to the sides. But if I'm ever at a point where, along, say here, if I look out, this peak is actually higher, so it selects from there instead of where my right finger is. It selects from the edges that balance to here instead of here at the center along the m equals 0 line. And let us make sure. There we go. I closed my computer and it went, no, I don't want to stay on anymore. Oops. All right. So when I do that, what do I get? So again, we go through and we ask each of the deltas and each of the temperature differences, so I can try and reproduce this graph over here, the phase transition. When I do the Prekoppel-Lindler, why did it go away? Don't. Why are computers like this?
Wow, that took a while for a PNG to load.
Oh man. I guess it's struggling because it's just booting up again. Yay, computers.
Hi, Ben. How you doing?
Hey. So one of these days, I feel like we should talk about. I just saw some, one papers about quantum supremacy, apparently, supposedly finally being produced. Also, wow, that went up.
Yeah, we really need to talk about that.
I want to read through that. It looks like fun. Oh, I love that eye roll. Anyways, so, right, again, I should be saying, aha, my phase diagram should be showing, right, this curve should be this curve. And largely, in fact, I look at this and I go, wow, this matches really well.
Except
all the way up to here.
Right.
So this is a fact of how we map between energy and temperature. Effectively, as you crush down, as you shrink the quadrupole moment, that center point squeezes in until eventually, as you push delta equal to 0, there is a single point that is along the m equals 0 line, right? If I push delta equal to 0, I've got a single point. So there's only one thing you can ask that about, and then obviously as that crushing down to a single point happens continuously, but it happens pretty quickly. So swoop, right? That's where so obviously this method has its own problems, which we can explain away It captures the most it captures most of the lying, which would be nice, right? Now, obviously, there is the distinction, right? I've just given you two colors, right? Phase transition, not phase transition. But here we've got three things we care about, right? Second order, first order, and the two transitions between the two. And here's that fun kicker. This is where we get to the coup de grace, right? The picture that as I've said, defines the most I have ever learned about a thing that no one else has ever learned about. The most PhD thing there ever was.
That's pretty cool, actually.
Yeah. Is this picture.
Ah.
And it is simply the two pictures overlaid on top of each other. Right? And actually, let me resize this a little bit so it's not as monstrous comparatively. The fun. I'm so bad at this. You know, it's harder than you think.
You know, you can do the same thing on the left and right.
I know. I should be able to. I could just do it one at a time. I wanted the corner just so that I could do it efficiently.
Oh, yeah, okay.
That's kind of what I was going for. That's why I'm stumbling here.
Come on, use those StarCraft skills.
Oh, yeah. All right, so here we have reproduced. I notice when I use the local concavity method, because locally it'll see the non-support and go, no, it fails here. It fails here. I know the difference between these two. It doesn't fail, it does fail. It's great. And so it's able to capture this. What's most interesting is this point here where it diverges. If you fiddle with this, it maps exactly to that tricritical point there. So there we go. We've built up to this picture where I can say, oh, okay. First order, second order phase transitions happen when I can sense locally the phase transition has occurred. That locally there is evident that locally the density of state says, no, I am not log concave here. There's going to be a phase coexistence. Second order, you'll have a smooth phase transition if I come into it from that region. But if I come into it in a way that the density of states can't locally tell you, and instead you have to look at the whole thing. You can't just look at a single point on the density of states. You have to look at the global properties of the density of states.
Okay.
If you come into it that way, that will force, as far as I can tell, I think this is going to require more math to explore, but it appears that will force a first order phase transition. And that's what this guy here is. This guy here is that point right there where delta is equal to about 0.463. And, you have your magnetization allowed to move to whatever. This is the tricritical point of the BEG, Blume-Emery-Griffiths model on superhelium. Right exactly where we go from having locally apparent phase coexistence to globally only known phase transitions. So there you go. This is science. This is the process of science, and I cannot show you the ugly bits of fun. There's a whole set of pictures because for a while you can approximate the choose functions with Stirling's approximations to make sure you get really, really continuous things instead of polygamma functions. For a while I was using that, and that created a mostly good thing, but then there's like splinters of stuff that's wrong.
Right.
And well, actually,
because it just doesn't belong.
Yeah.
Yeah.
It's this picture here. Mostly good, but this little bit at the bottom and also the bit up here is wrong.
Now, is that method, is it possible to be faster in some ways? So you could use that as a first pass?
Yeah, and that's exactly what we did. It was just like, okay, it's easier to do the computations, it's easier to do the actual derivatives and stuff, and then realized like I figured out small errors, but then there were still splinters of that little bottom piece that shouldn't exist. And eventually I went to the thing because I realized, wait a minute. Since we are looking at the density of states across all the values that go on the bottom of that equation of state, that's exactly where the Stirling approximation falls off. It's not by much, but it's by enough for it to fail. So you had to go to the full order one. That was science. Knowledge in the making of just like, no, you need to make sure that you have these proper things. Because even if you have only an approximation, wow, you can still get pretty close to like what it actually should look like.
Does it actually still get the tricritical point correct?
Yeah, where the farthest that the local method goes is right where it maps to. What you'll notice is that there's some more disagreement, which is just like, that's kind of weird. It turns out it's just a numerical effect from the fact that you're using an approximation, right? When I use the actual function that defines my BEG, that goes away, right? Well, plenty of lessons of, always take with a grain of salt your results when you're using approximations.
Of course.
Welcome, audience. You have seen some cutting edge science on a new math tool, saying, "Hey, we can understand phase transitions. We can understand how to find when these complicated systems change their behaviors wildly, potentially with very small, subtle changes in the environment that they're placed in with respect to. And you can find out when these changes will happen with nothing more than being able to count the configurations that your system can pop into.
Nothing more.
Nothing more. Do you want to get into the discussion of how hard it is to try and account for the things that are beyond nothing
I can
more?
already tell you how that's hard. But still, this is still pretty awesome.
It's some fun stuff. But yeah, I figured going through this process of this specific model, right, really can give you a flavor and a scene of how it actually works, because it is really complicated stuff trying to think about a density of states, like mathematical object,
and that pitfall,
and then on top of that, and then how approximations are off.
Yeah, because I could see somebody taking your method and be like, wait a minute, and not neither of these graphs getting that other one that just
the local version.
Just be like, I saw this crap on YouTube and I should have known better. It's like, no. Yeah.
Yeah. And like exactly that, because when I showed in that talk, I used exclusively Hessian, the local concavity, and occasionally, like like the icing model is in terms of a bunch of sums still, because it's really hard to figure out how to figure out what that sums to. Again, turns out that counting and summing things are actually incredibly difficult. I have an entire book on the ways that I've tried to solve that. It's awful. And it doesn't, it goes into a thing called a hypergeometric function, and then trying to figure out a sum over that. And it's those are, and I think it's important for anyone watching this to know, when a mathematician tells you that they are scared of a mathematical object, it's nasty looking. It does some real crazy shit. But yeah, it's great. Also, since we're going into the details before you actually transform between energy and temperature, right? What you most naively first get is this guy.
Ooh.
Yeah, so you got to be like, oh, well, what the heck? This looks nothing like it. And you got to realize, well, okay, it's not. This should just be straight energy. Again, thank you, Python. Right? These are all energetically unaccessible. That's requiring much more energy than you can reach, and yada, yada. But the processes of science is messy. Even when you're working on stuff that you can do with pencil and paper, it is a hard time. But I'm not going to lie. It really is neat to look at something and go, yeah, I realized that. No one else has done that, has realized that before.
That's cool. That seminal moment.
Yeah. I tell you what, working on this, it's the first in 4.5, well, I guess 4 years is about when I started on that. Well, yeah, about 4 years. About 4 years. That's the first moment where I'm like, wait a minute, I discovered something. Oh, that's pretty cool.
It is very cool, man. Well,
yeah.
Happy holidays, and may your phase transition to 2021 be smooth.
Amen to that.
All right, cheers, my friend. That was awesome.
Cheers.
All right.
Yeah.
It's time to be a carnivore.
Amen.